Good morning. Today I'd like to continue talking about slightly silly stuff. We're going to look at coordinate systems where the coordinate axes and things parallel to them are still straight lines, but not of the nice Cartesian type that we've seen before. Shortly after this, we're going to find out that all of this stuff has been much less silly than a person might think, but we'll see that when we get there. We've been discussing Cartesian coordinate systems. If we have two Cartesian coordinate systems with a common origin, we have figured out that the equations that relate one set of coordinates to the other must involve an orthogonal matrix. We can't have any objection if somebody else decided to set up a Cartesian coordinate system and called this red straight line their x-axis. One possible point of contention is the person then declares that their y-axis is this blue straight line. You object, those axes are not at right angles to each other. That's true, but it's not a problem. I just need two independent directions in the plane to locate points. This, in a certain sense, would be a good coordinate system. It's not related to the original one with an orthogonal transformation, though, because it's not Cartesian as such. In xy coordinates, if I look at the places where y is 0, that would be the x-axis. In terms of this new coordinate system, that might be these points. In xy's, if I look at places where y is 1, that's a straight line parallel to the x-axis, 1 unit perpendicular-wise from it. The corresponding thing in the new coordinates might be this line, and then that one, and that one, in analogy to lines that are parallel to the x-axis in Cartesian coordinates. Likewise, you could draw in lines of constant values for the other coordinate, and you would get this picture. I'm thinking of the red and blue straight lines as being lines of constant new first coordinate or new second coordinate. Now, immediately, there's all sorts of objections that jump into your head. For one thing, if I use these kind of coordinates, it's not at all obvious how I'm supposed to calculate distances and stuff like that. We'll have to look into that. More interestingly, back in third semester calculus, they made this big deal out of parallelograms and parallelepipeds. We're now beginning to see the reason for that. In Cartesian coordinates, region bounded by constant x values and constant y values are rectangles. In these new coordinates, that's not so. The region bounded by lines of constant coordinates are typically parallelograms. If I was in 3 dimensions, I would have parallelepipeds. So all of that seemingly obscure and obsessive stuff in Calculus 3 having to do with parallelograms and such, there was a reason for it. Even though these other coordinates, even though these new coordinates are not Cartesian, the coordinate axes are still straight lines. In the original coordinate system, a straight line was a linear expression involving x and y equaling a constant. So each one of these blue lines must be something of that nature. Every one of the red ones must be something of that nature. This means, in the same way that we thought about it before, if I relate coordinates of points in the original XY coordinate system to these new coordinates, the red and the blue ones, the relationships must be linear relationships. It won't be a orthogonal linear relationship unless the new coordinate system is Cartesian. That is to say, the axes meet at right angles. I'll call the coordinates of the Cartesian system x and y. Here's the x-axis, there's the y-axis. I'll call the coordinates of the new system x bar and y bar. Here is the x bar axis, and here is the y bar axis. The graph of the equation y equals 0 is the x-axis. The graph of the equation x equals 0 is the y-axis. The graph of the x bar axis is y bar equals 0, and this will be x bar equals 0. If I give you a point, it has a single x and y coordinate. If I give you x and y coordinates, there's a single point. If I have a single point, it lies on exactly one blue line and on exactly one red line. So there's a relationship here. If you give me xy coordinates, there's exactly one point to go with them. That one point has exactly one pair of x bar, y bar numbers to go with it. So given an xy, there's a single x bar, y bar to go with it. Given an x bar, y bar pair of numbers, there's a point in the plane. That point in the plane has a single pair of numbers x and y to go with it. So if you give me x bar, y bar, there can be only one xy to go with it if this is in fact a legitimate coordinate system. There must be constant numbers a, b, c, and d so that x bar equals ax plus by and y bar equals cx plus dy. In matrix form, I could write it like this. There must be numbers that don't depend on x bar or y bar, so that if you were to tell me the x bar, y bar coordinates of a point, I could put those numbers into this formula and tell you the x and y coordinates, which I can also write in matrix form. For any point with unbarred coordinates x and y, xy must equal EFGH times x bar, y bar. But x bar, y bar is ABCD times xy. So I can write that down. xy is the identity matrix times xy. xy equals this. So if I subtract the right-hand side from both sides, the result on the right must be 0. Both matrix column vector terms have xy as a factor on the right, so I can factor it out. So this is very interesting. This says the matrix inside this large bracket multiplied by xy must be the column 0, 0, This has to be true regardless of what the x and the y are. I'm going to make up an abbreviation for identity matrix minus EFGH times ABCD. I think I'll call it capital R. Capital R multiplied by xy is 0, 0, no matter what the xy is. In linear algebra, there is no concept of dividing by the column xy. So I got to be a little bit more careful than that. I want to conclude that R is the zero matrix, but I can't divide through by xy. That's not going to work. I'm going to call the entries in matrix R alpha, beta, gamma, and delta. I'm going to do a trick that's very similar to those pick the specific points and manipulate it tricks that we were doing the other day. Firstly, I'll look at what happens if x is 1 and y is 0. This equation will have to be true because it's supposed to be true no matter what x and y are. Because of the way we multiply 2 by 2 matrices times a column vector with two numbers in it, go across the column, row down the column, alpha times 1 plus beta times 0 is alpha, gamma times 1 plus delta times 0 is gamma. This is supposed to equal 0, 0. The only way that's going to work is if alpha is 0 and gamma is 0. So I know those two numbers must be 0. Making an exactly similar argument using 0, 1 for the xy, it turns out that beta must be 0, also delta must be 0. So R, which is alpha, beta, gamma, delta, works out to be 0 there, 0 there, 0, 0. All of the numbers in the R matrix are 0. R is the 2 by 2 0 matrix, just like we thought it ought to be. But R was the identity matrix minus that matrix. If that's 0, then I must equal EFGH times ABCD. That means that EFGH and ABCD are matrix inverses of each other. So the coordinate vector x bar or y bar is this matrix little a, b, c, d times xy. I'll make up a name for that 2 by 2 matrix. I'll call it capital A. X bar, y bar is capital A times the column of x and y coordinates. And because of what we figured out about the relationship between ABCD and EFGH, I can just go on and write the unbarred coordinates, take the inverse of matrix A, and multiply it by the column of barred coordinates. If you remember your linear algebra, now this should come as absolutely no surprise to anybody. Suppose that we're in the Euclidean plane. I have 2 points, P and Q. Using Cartesian coordinates, the coordinates of point P are x1 and y1. The coordinates of point Q are x2 and y2. I want to calculate the square of the distance between those 2 points. We know, though, that we can write the coordinates in one system as linear functions of the coordinates in the other. So P also has an x bar, y bar coordinates. Also Q does. I want to think about how the distance calculation would go. If you were to tell me the x bar and y bar coordinates at point P, I could put those numbers into these two formulas and tell you what the x and y coordinates are. So this is another way to express the Cartesian x and y coordinates at point P. You can do the same for point Q. These expressions look very strange. I want to emphasize this number is x1, this number is y1, this number is x2, this number is y2. I've just expressed the values of the unbarred coordinates in terms of the barred coordinates. That means another way that I could calculate the square of the distance from P to Q would be to take this number, subtract that number, square it, take this number, subtract that number, square it, and add them together. Pardon me. So on the one hand, the distance squared between P and Q is this expression, which I'm just going to write as shorthand, the change in x squared plus the change in y squared. This is nothing but the Pythagorean theorem. Because the coordinates that we're calling the barred ones are so weird, the formula for the distance squared is much more complicated looking, but it's not as bad as it looks. I can group like terms together and find out that the distance squared is this expression, which is still pretty ugly, but we'll simplify this in the same way we did the other one. I'm going to call x2 bar minus x1 bar delta x with a bar over the x. It's literally the change in x bar. I'll call y2 bar minus y1 bar the change in y bar. I'll call it delta y with a bar over the y symbol. This looks pretty bad, but again, we'll be able to combine some terms. There will be an e squared plus g squared delta x bar squared. There'll be 2ef plus 2gh multiplied by delta x bar delta y bar. There'll be f squared plus h squared times the square of delta y bar. There are immediately 2 points of interest here. Firstly, the coefficient in front of delta x bar squared and delta y bar squared need not be 1. That's because the perpendicular distance between two of these parallel new coordinate axes lines need not be 1. More interestingly, though, there's a cross term. There is a delta x bar, delta y bar term. This doesn't happen in Cartesian coordinates. It's going to be a long time before we come fully to grips with that, but basically it's because the barred coordinate systems are not at right angles to each other, whereas the Cartesian ones are. Right angles, something not being there. Right angles, something being 0, If you've had third semester calculus, this should make something in your memory slightly wake up. We'll come back to that later. Both of these formulas are quadratic in a sense. The way the changes in coordinates show up is either the square or one of the changes multiplied by the other one. So we say that this is a quadratic relationship between the square of the distances and the changes in the coordinates. The major difference between these two things is this coefficient isn't 1 necessarily, but that one is. This one is not necessarily 1, but that one is. And in Cartesian coordinates, I don't have a delta x times delta y term running around in it. I can find a certain commonality if I think about this a certain way. I can write the Cartesian distance squared as 1 times delta x squared plus 0 times delta x delta y plus 0 times delta y delta x plus 1 times delta y squared. It looks very odd to write it like that, but I have my reasons. In a similar way, I can write the distance squared using the barred coordinates as e squared plus f squared times the square of the change in x bar. I have 2 times that delta x bar delta y bar. So I'll write that in two pieces. GH plus EF delta x bar delta y bar plus GH plus EF delta y bar delta x bar. We'll find out why we want to write it like that in a moment. Plus f squared plus h squared times delta y bar squared. If I want to use linear algebra thoughts, I can write this in a very suggestive way. Write delta x delta y as a row vector here, delta x delta y as a column vector here. Oh, and I'm using the word vector in the linear algebra sense of the word, and put the identity matrix in the middle. If you were to multiply this out, just the identity matrix times the column would be 1 times delta x plus 0 times delta y in the first position, delta x, and 0 times delta x plus 1 times delta y in the second position, which would just be delta y. You would take the row delta x delta y, multiply it by the column delta x delta y, and get delta x squared plus delta y squared, which is, in fact, the square of the distance between P and Q. In exactly the same way, I can represent the distance squared as a row involving changes in the barred coordinates times a matrix times a column involving the changes in the barred coordinates. So if I tell you only the changes in the barred coordinates, I tell you that delta x bar is 6 or something, and delta y bar might be 4 or some such things. I'll construct this 2 by 2 matrix using the formulas that relate the bar and unbarred coordinates. None of these numbers depend on any of the coordinates. They're constants. There will be a constant 2 by 2 matrix so that I do row of the changes in coordinates times matrix times column of changes in the coordinates, and this will give me my distance squared in terms of the changes in the barred coordinates, not the unbarred ones. On a philosophical level, this is very interesting. Coordinates, matrix, coordinates. Coordinates, matrix, coordinates. The complicating factor is that these numbers are not as nice to look at as those numbers are. From our human perspective, Cartesian coordinates are the nicest of all coordinate systems. The matrix in the middle just turns out to be the identity matrix. If I'm using coordinates that are not Cartesian, the same kind of thing happens, but the matrix in the middle isn't as nice. Later on, we're going to have a very fancy set of words to use with this. We're going to call the numbers in that matrix the components of the metric tensor in Cartesian coordinates, and these numbers are going to be the components of the metric tensor in the x bar or y bar coordinates. We actually said the t word. We have a bunch of work to do before we can get anywhere close to regularly using the t word. So coming up next, we will drop all pretense and start thinking about space-time diagrams. In the meantime, I hope everybody has a good day, and I'll talk to you again soon.